anything I decide. Hello. Now I'm on. I wasn't on that whole time. Okay. Here we are. We're getting there. We're getting to Green's theorem. We're getting there. We're almost to Green's theorem. Green's theorem is sort of baby Stokes' theorem. But last time what I showed you was path independence, okay? And what did I do? Let's not worry. So I talked about energy conservation, and I derived energy conservation for you. In fact, I said that this motivates the definition of energy itself. That's how we get energy in the first place, through that calculation that I provided for you. But from the perspective of calculus, the issue that we were concerned with is what's going on with this vector field, this work line integral that we have to do, the integral over the curve of f dot dr dt dt. And what I said was when f is equal to the gradient of some other function, little f, then we found the following, okay? And I'm going to redo this step by step. And I'm going to redo this. And when I redo something, you've done it. You've probably taken notes on it last time. It's in the book. If you want to pause and just listen to my words and not run through the notes, it might be a good time to do that. And just to hear how I describe it, okay? Because there's going to be no new chalk spilled, but hopefully I'll be able to elucidate this better, okay? So again, the issue is this. Consider f being the gradient of a scalar. Therefore, the work is equal to the integral along the curve of that gradient of that scalar, little f, dotted into the velocity field associated with the curve. Now this is, I keep using velocity, but this could be just any parametrized curve. It doesn't really have to come from Newton's laws. This is a completely valid integral to do in the first place. And this is dt, okay? And so if we have a curve, that means we have some r of t. So I consider my r of t here. And this is, say, r at t0, the beginning time. And then r of t1 is at the end time. And you're going between t0 and t1. OK? Now, the point here is that this dot product is the directional derivative, is a directional derivative of f in the direction of the curve. Okay? So what you should imagine is that there are some contours associated with little f. So if we were going to plot, this is little f is equal to 0. This is little f is 1. This is little f is 2. This is little f is 3. This is little f is 4. Then the gradient of f is the vector field, which is everywhere perpendicular and which measures how much it is changing in that direction, that perpendicular direction. So here, the vector field is about this big. And here, here's a question. Would it be bigger here or less? If this is 0, little f is 0, f is 1, f is 2, f is 3, and f is 4. Let's compare the vector here with the vector here. OK? Very simple question for you. I know it's perpendicular. I know the direction of the vector gradient f here. Would it be bigger or smaller than the vector here? And why? Does anybody want to venture an answer to that? Sir?
It would be smaller because there's a smaller difference between 2 and 3 than 1.
It would be smaller because there's a smaller difference. See, there's a smaller difference. So the difference between f here and f here is 1. And the difference between f here and f here is 1. But the distance over which it changes is smaller than the distance over which it changes here. So it's actually bigger. OK? It's actually bigger because you're making the same amount of change in a smaller step. OK? The change here is 1, and you're doing it in this wide step. And the change here is 1, and you're doing it in a narrow step. So the rate of change of f in this perpendicular direction is larger here But thank you for trying, though. Thanks. And it's counterintuitive, actually. So, by the way, where the contours, when you have a contour plot where the contours are bunched up really close, that means the gradient is really high. Okay? So bunchy means big vectors. Spread out means smaller vectors. Okay? So this is the directional derivative of f in the direction of the curve. And so if we were to go to a point along the curve, and here's this point along the curve, and the perpendicular to the contour, I'm going to try to draw a perpendicular as this. So grad f looks like that at that point. And the velocity is tangent to the curve, so it must look like this. Okay, I won't draw them that they're exactly the same length. And the dot product, of course, is like we said, the shadow of this vector on this. Okay? So what you can think about is that there is a tangential direction to the curve. And let's just do an imaginary normal direction. So this is the perpendicular, not to the contour. This is the perpendicular to the curve, okay? So this is the tangential direction to the curve. This is the perpendicular direction to the curve. And you can resolve f as its component in this direction and its component in that direction. In fact, that's what I've drawn. The components along the curve direction and the components to the normal in the perpendicular to the curve direction. And so, I mean, plausibly, you can think, oh, this is the component of the change of f in the direction along the curve. This is the component of the change of f in the direction perpendicular to the curve. So this dot product, which picks out this component here, has something to do with the change of f in the direction along the curve. Okay, that's just sort of hand-wavy, right? And I always ask you to consider units. This is units of little f divided by length, multiplied by length over time. So this is the units of little f divided by time. The rate of change of little f as you go along the curve. Okay? And the way I wrote it out was with chain rule, which is the following. I'm trying to make the following statement. I define this other function, and I can't use capital F now. Let me use V. No. Can I use V? I'm going to use cursive F. Cursive F. Allow me to use cursive F, okay? Cursive F is simply a function of time, okay? That's F. And what do I mean by this? I mean that this is little f evaluated at x of t, y of t, z of t. As you'll see, I'm effectively repeating what I did last class. But I want to do it to emphasize that what you're seeing up there in parentheses, or in those parentheses up there, is a reflection of the chain rule. Now, little f is only a function of time, so I can take the time derivative of both sides. df dt. Well, big F, its natural arguments are x, y, and z, but I'm evaluating it along the curve x of t, y of t, z of t. So in order to do that, I have to take the derivative of little f with respect to its natural argument and then evaluate it along the curve. And that's what I mean by evaluate it along the curve, r of t. And then I have to multiply by dx dt. That's the change of f in the x direction, multiplied by the x velocity, plus the change of f in the y direction evaluated along the curve r of t dy dt, plus the change of f in the z direction evaluated along the curve r of t dz dt. I do this evaluation to emphasize that these little f is a function of x, y, z, the Cartesian variables x, y, z. But in this, on the right-hand side here, this must be only a function of time. So you must evaluate those Cartesian variables on the curve. And that'll give you, this will be a function of time if you evaluate it at r of t. Okay? And this is what we mean by the gradient of f, 1, 2, 3, dotted into dr dt. 1, 2, 3. So that's the full sort of teasing out the details of chain rule. Okay? That's what you did, and that's why you did it in Calc 21C. Now, what does that mean? It means I can replace this gradient dotted into this dot product, into this velocity, with this quantity, which is what is defined as, with this quantity over here. Therefore, that work, that one right there, is equal to the integral from t0, the beginning time, to t1, the end time, of, well, I'm replacing it all with df dt. So this is d by dt of f of t. And then I have to integrate that with respect to time. And that is huge, because I've recognized that that complicated line integral really turns out to be a very simple 21b integral. And it's poised to use fundamental theorem of calculus. Okay? Well, by the fundamental theorem of calculus, the integral of the derivative is equal to the function evaluated at the upper bound minus the function evaluated at the lower bound. But now we do that last step, which is to recognize f of t is simply f of x of t, y of t, z of t. And so this is f of x of t1, x of t2. Oh, so what am I doing? Autopilot. Y of t1, z of t1, minus f of x of t0, y of t0, z of t0. That's it. And this was the change in that potential. And I want to just give you two pieces of notation. As written up there, if capital F is a vector field, and if you can write it as the gradient of a little f is called the potential. In physics, we define the potential energy. We let this, if F is a force, then we write negative gradient of V. And this is called the potential. But this is called the potential energy. And if you recall from my derivation of from last time, the reason we had the negative here, why was the convention negative? Because when you bring that term over to the other side, it becomes a positive on the other side when you put it side by side with the kinetic energy. Okay? And then you get kinetic energy, whatever that was, mv squared, plus potential energy, v, is constant in time. Okay? That's how that works. Okay. So this is the story about path independence. Because this tells you that the integral of the vector field, right, this line integral of the vector field, is independent of path, because it only depends on the beginning point and the end point. It doesn't depend on how you got there. That's not true. This is not true of all vector fields. But it's true of vector fields that can be written as the gradient. And there's something else. There's something else that's true. If you end up at the same point that you started off from, it's 0. Which means that, oh, wait a minute. Remember how I said the definition for circulation and the definition of work were the same thing. So the circulation of this kind of vector field is also equal to 0. Well, it's always equal to 0. Okay? So the circulation of a vector field f, which is the gradient of f, is equal to 0. So such vector fields are called, they're either called potential vector fields, because they arise from a potential, or they're called conservative vector fields because they give rise to conservation of energy. Okay? So that's the structure of this whole thing. Now the question, the main question here is if, so this is a powerful tool. If you can do this, this is a powerful tool. Because think about it. If I can figure out, if I'm given a capital F and I can figure out the little f, I've essentially done the integration. Because I just got to evaluate that little f at the endpoints and I'm done. Okay? So the tool is, it would be nice to figure out little f. Okay? So the question is, when is capital F equal to the gradient of little f? When is capital F equal to the gradient of little f? So that is to say, if you are confronted with a capital F, how do you know or not know, or know not, or know that it is not, the gradient of a function? How do we know that? And this construction will tell you. This is how. This is the story. Okay? So imagine we have f is equal to m I hat plus n j hat plus p k hat, where m, n, and p are functions of three variables, right? And they're just three differentiable functions. You're given some arbitrary vector field. These are the components of that vector field. So for f to be equal to the gradient of a function, in order for this to be true, then what does it mean? Well, that implies m is the x derivative of little f, right? Because that's the x component of the gradient. Then n is the y derivative of little f, and p is the z derivative of little f. If this is going to be true, this has to be true. These three statements have to be true. But look at these three statements, everybody. You have three arbitrary functions. Right? So arbitrary vector fields can be three arbitrary functions. But they're all related to this other function, if it's a gradient. So that means they all have to be related to each other. Right? There's no a priori, there's no reason before the fact that m should be related to n should be related to p. They'd be crazy functions. That's a vector field, right? They have no relationship to one another, but they can be put together to make it look like a vector field. But if they're a gradient, then this is the x derivative of another function, and it's this is the y derivative of another function. This is the z derivative of another function. That means they're all m, n, and p cannot be completely disconnected from one another. They must be related to one another. Okay? And how are they related to one another? Well, it's almost screaming at you. It's almost screaming at you. Okay? Look, if you take the y derivative of the m equation and the x derivative of the n equation, let's see what we get. dm dy is equal to d squared f dx dy, and, so this is nota bene, and dn dx is equal to d squared f dy dx. So what does this say? It said, take the x derivative first and then the y derivative, because that's what I did. I took the y derivative last. So I just took the y derivative of the m equation, and then I took the x derivative of the n equation. That's all I did. Now, how are they related to one another? How are they related to one another? Well, if a function is to be differentiable and twice differentiable, then the order with which you take the derivatives must not matter. This says do the x derivative first and then the y derivative. This says do the y derivative first and the x derivative. They have to be equal. The order must not matter. Okay? Therefore, dn dx equals dm dy. do this again with, we're going to do it with m and p. The y derivative of that, the z derivative of that. They must be equal. The x derivative of that, the x derivative of that, the z derivative of that. I can't read very well upside down like this. The z derivative of that and the x derivative of that must be equal. So dp dx is equal to dm dz. And maybe you can see that there's a third relationship. And here's a third relationship right here. I have to take the z derivative of this and the y derivative of this. So I want to make sure I got them all right. And m, p, and p, and this one has to be m. I got them. I didn't put the order the way I wanted to do it, but it doesn't matter. They're equalities. So it's going to be dn dz is equal to d. Let me write it this: dp d y. There we go. There you go. Okay. I should have switched the order around a little bit. Did I get them all right? You guys, you're happy with them? Okay, good. So, note also. Let me just note something, okay? This is for three-dimensional vector fields. What do we have with two-dimensional vector fields, really quickly? Note also for 2D, in 2D, p is identically 0. That means identically 0. It's 0 everywhere, okay? 2D, p is identically 0. And dm dz is equal to dn dz is equal to 0. In 2D, nothing depends on z, and the z component of the vector field is 0. That's all it's saying. Okay? So, in 2D, this is equal to 0, this is equal to 0, this is equal to 0, this is equal to 0. These are all satisfied. In 2D, the only thing you have to check is this term. Okay? The only thing you have to check is this term. So let's check that term. So only check dn dx equals dm dy. Example. Example 1. Okay? Constant vector field. What happens for a constant vector field? Well, its derivatives are 0, right? So it's satisfied for a constant vector field. So every constant vector field is a gradient. Okay, e.g. 1, u vector, or sorry, f vector equals I hat, a very simple constant vector field. Check, yes. Because m is equal to 1 and n is equal to 0, the derivative of 1 is 0, that goes away. Okay, constant vector field, that was easy. Vector field 2. Let me write down my canonical explosion type vector field, the radially pointing outward vector field, okay? So I think I wrote it something like alpha x I hat plus y j hat, okay? In this case, m is equal to x and n is equal to y. dn dx is equal to 0 and dm dy is equal to 0. Therefore, check. F is the gradient of little f. F is the gradient of little f. Okay? I'm going to tell you what little f is right now. So I'm going to split the board again. Let me write it here. Check. Therefore, capital F is the gradient of little f. What's little f? Well, remember, this is going to be d little f dx I hat plus d little f dy j hat. So let me actually go ahead and compute d little f dx, little f, okay? And how am I going to do it? Oh, I forgot my alpha, everybody. There's the alpha, there's the alpha. I just dropped the alpha. Well, if it is the gradient, that means I know I can write it in this form. That means I know that alpha x is equal to df dx. Right? That's m is equal to df dx. And I know that alpha y is equal to df dy. This is a very, very simple differential equation that you can just integrate in one go. That means, right, f is equal to alpha x squared over 2, right? Because the derivative of alpha x squared over 2 is, the x derivative is 2 alpha x divided by 2, so it's alpha x. So that's that. Plus a constant anything that doesn't depend on x. So it's not truly a constant, because things can depend on x and y here. Anything that doesn't depend on x. So any other function of y. So let me call it c, like the constant, it was not constant, of y. Right? Because if I take the x derivative of this equation, I get alpha x, and I take the x derivative of this, I get 0. So when we say constant, and we did the antiderivatives, we really meant doesn't depend on any other variable, or on that variable. On that variable, can depend on the other variables. Okay, so this is f that I got from this equation. And then I say, wait, I don't know f completely. I've got some arbitrariness to f. I would like to resolve that arbitrariness, thank you very much. So what I do is I substitute this f into this equation. Let's see what we get. So when I substitute that f into that equation, I have my left-hand side is still the same. My left-hand side is alpha y, but my right-hand side becomes the y derivative of alpha x squared over 2, which is 0, plus the y derivative of this c of y. Okay? Some c of y. Now I take the antiderivative of this equation, and I'm left with c of y is equal to alpha y squared over 2, plus a constant that, could it depend on x now? Well, I already figured out the x dependence. This is truly a constant right now. This is truly a constant, constant, constant. So let me put it together, and I've got little f is equal to alpha x squared over 2 from there, plus y squared over 2 from here, plus any arbitrary additive constant. Because you can add any constant to the function f, and when you take its gradient, it's always going to be 0. So this process only ever gives you little f up to an additive constant. And that's the same additive constant, that's the same concept that you get in regular 21b integrals, right? The antiderivative gives you an arbitrary constant. Take the gradient of this, and you see clearly it is the function that we got over there. It is clearly the function we got over here. Now, let me, by the way, this arbitrary potential. It's no coincidence that in electrostatics you talk about the voltage or the potential, right? And the electric field is the vector field, and the potential is the gradient of the potential is the electrical field, right? So this is exactly like the voltage drop in some sort of capacitor, as an example, okay? So if you've ever taken electrostatics, that's what you get in a voltage drop. If you ever think of voltages, that's what you got. That's a potential, okay? So let's plot contours of little f. So here's x, and here's y. And if you look at this thing, sometimes we do surface plots. This is a paraboloid. right? This looks like a parabola of rotation. F is equal to alpha x squared plus y squared over 2. X squared plus y squared, well, they're circles, but if you take any cut over through that surface of plotting this, like say the y equals 0 cut, that's f equals x squared over 2, alpha x squared over 2. That's a parabola. And that's a parabola. And any rotation, if you rotate it on any angle, you'd still get a parabola. This is a paraboloid. Okay? And the way what this thing looks like is, hey, this thing is constant on circles. Here's f, maybe f equals 1. Okay? And f equals 2 would be, oh, I don't know, f equals 2. They're going to bunch up. F equals 2, f equals 3, f equals 4. I'm trying to make them bunch up. I'm doing it okay over here, but not on the other side so much. F equals 5, f equals 6. They're bunching up, okay? Those are circles that are bunching up. They're supposed to be getting closer to one another, okay? They're all circles centered at the origin. That's little f. And what's the vector field capital F? Well, because it's a gradient, it's pointing outward from each of these contours. And it's getting bigger. Remember what I said, when it bunches up, it gets bigger. Okay? And you see that it gets bigger because that vector field was alpha x I hat plus yj hat. Its magnitude is getting bigger as you get farther from the origin. Its magnitude is alpha times the square root of x squared plus y squared. Okay? This is a gradient vector field. Okay. And this, by the way, this exact process that I just did is exactly how you compute the potential if you've figured out that a vector field is the gradient. You do exactly what I did. But if you have a three-dimensional vector field, you just have to do this integration 3 times. If you had a three-dimensional vector field, you would get f is alpha x squared over 2 plus some function of y and z. And then you would put that in here, and then you would get some function of z. This would be a function of z. And you would do it a third time. But it's exactly how you go about calculating the potential. Okay? You just have to do it carefully. If I have time, I'll do one more of these examples before the end. But I want to show you another vector field. Okay? And the other vector field maybe I'll show both other vector fields. Okay, example 3. That was 1, 2. Here's 3. My vector field is f is equal to omega, because I like that one, negative y I hat plus x j hat. And you remember that this was the swirl around vector field, right? So this is the vector field whose magnitude increases linearly with distance away from the origin. And it's always swirling around, okay? Okay. Now, m in this case is negative omega y, and n is omega x. N is omega x. And look what happens here. dn dx is equal to omega, and dm dy is equal to negative omega. Therefore, dn dx is not equal to dm dy. Therefore, f is not equal to gradient phi at gradient f. Vector field f is not equal to gradient of little f for any little f. It's not a gradient. It's not a gradient. Not a gradient. Which also means that there's no contours that I can put here and say that the vector field is always perpendicular to those contours. But there sort of are in this case, but it doesn't, they all kind of collapse at the origin. They all collapse at the origin. But it's not a gradient in general, okay? This is the canonical vector field, the basic example of a vector field that you cannot write as a gradient, which is why I busted up the vector fields into these basic vector fields, because I wanted you to see what the basic ones were. And if you can stare at this long enough and think about why that one was a gradient and why this one's not a gradient, you'll get a sense of what we're measuring when we do gradient, right? This one is swirling. Gradient is pushing things out. Okay? Okay, the last vector field was, a little, was it nicer? I don't know, was it a little nicer? The last vector field is f is equal to alpha xi hat minus yj hat. And just to do this example, m is equal to alpha x, n is equal to alpha negative alpha y. And in this case, dn dx is equal to 0, and dm dy is equal to 0. Okay? What do I want to say about this one? Well, this one's fun. I'm just gonna draw it out. You remember what these vectors looked like, I hope, from before. So since these guys are equal to each other and they're equal to 0, we have df dx, which is the potential, must be equal to the first component, and df dy must be equal to the second component. N. So you take the antiderivative of the first one, df dx is equal to alpha x. That's the first equation. That tells you if you take the antiderivative, you're left with f is equal to alpha x squared over 2 plus any function of y. Then sub into df dy, which is the second equation, equals negative alpha y. And this tells you, if you substitute this into the left-hand side, the derivative of this is 0, and the derivative of this is dc of y dy is equal to negative alpha y. And that tells you that c of y is equal to negative alpha y squared over 2 plus another arbitrary constant c. And so f is equal to alpha over 2 x squared minus y squared plus any arbitrary constant. And you see that f's, the little f's, are constant on hyperbolas. You just, to plot the contours of this, you just set f to be some number, right? Some number. And then you plot it, and you see, well, if f is 1, this is the constant, some arbitrary constant, so it's just some arbitrary number here. That's some hyperbola. X squared minus y squared equals constant is a hyperbola. So what you're left with are hyperbolas, in this case, that look like this. And remember, if you remember this vector field, it was like pointing in over here and pointing along hyperbolas over here. So it's kind of neat. The vector field is along hyperbolas of one kind and perpendicular to hyperbolas of the other kind. So these two hyperbolas, the hyperbola that goes like this versus the hyperbola that goes like that, are themselves perpendicular to one another. It's kind of fun. Okay? Just because I want to give you a bunch of examples and don't want to lead into a whole new discussion before your turkey sets in, we're going to, I'll just do one more example, okay? That's effectively the same thing, okay? So those were my basic examples. Those were like, how do you get this potential function from the basic vector fields? But if you do those steps for any vector field, it's always going to work, okay? So let me use this vector field here. So this is example, what are we on? Example 5. So this is example 5. Let f equal something like yz I hat plus xz j hat plus xy k hat. I'm going to do this in 3 dimensions and just work it all out for you. Okay? This is sort of the opposite extreme of the previous vector field. In the previous vector fields, you had x's here, y's here. These ones have no x's here, no y's here. not that it matters too much. You just go with the pattern, and it's straightforward, okay? It works out. So we have to test. So m is equal to yz, n is equal to xz, and p is equal to xy. And we have to test all the derivatives, okay? So I have to take the derivative of m. If you start ordering this, you have to take the derivative of m with respect to y, which is equal to z. And you have to take the derivative of m with respect to z, which is equal to y. Because you're taking the derivative of m with respect to the other variables. That's what those conditions, which I have since erased, the ones that are hidden on the board here, that's what they were telling you to do. Then you calculate dn with respect to x is equal to z, and dn with respect to y, with respect to z is equal to x, and then dp with respect to x is equal to y, and then dp with respect to y is equal to x. And those relations, those three relations that I showed you. Oh, oops, they were right there. That's so convenient. Okay. See, the second component with respect to the first variable, the second component with respect to the third variable, but not with respect to the second variable. The first component with respect to the second variable, the first component with respect to the third variable, but not with respect to the first variable. Okay. So I have to test each of these conditions, right? Well, they're staring at us, so I have to check, is dn dx equal to dm dy? Find it, dn dx is z, dm dy is z. Yes. That's one condition satisfied. Is dp dx equal to dm dz? Well, dp dx is y, dm dz is y. Yes, satisfied. And clearly dn dz is x, and dp dy is x, so it's satisfied. Therefore, all of these relations are satisfied, and therefore, we can write f vector is equal to the gradient of f. So therefore, f vector is the gradient of little f, which means that d little f with respect to x is the first component of f. D little f with respect to y is the second component of f. And d little f with respect to z is the third component of f. Again, d little f with respect to x is equal to the first component, which is yz. Okay? I just put what m is. I take the antiderivative of this with respect to little x. But y and z are independent of little x. So this is simply a constant from the perspective of little x. So this is f is equal to x, y, z, plus any function of y and z. Okay? So I need to call it something and not c. So I like to use g, because I got f and g. So I call this g of y and z. Okay? So I used the first piece of information here. You're done with it. Once you use a piece of information, you can't use it 4 times and expect to get more information. Right? You got to use the next piece of information. So you take this and plug it into the left-hand side. So this, let's call this first piece of information. Second piece of information is d by dy of xyz plus g of yz. That's plugging f into the left-hand side there, is equal to n, which is xz. OK? Well, if I take the y derivative of this equation, it's xz plus dg dy. And it's a partial derivative, because this depends on y and z. And that is equal to xz. Well, that's an easy equation to solve. Xz plus something is equal to xz. That means something is 0. So that says dg dy is equal to 0, which means that implies that g of y and z is equal to any other function only of z, right? Because this says it doesn't depend on y. But I said it could depend on y and z, and it says it doesn't depend on y, so it can only depend on z. So I'll call it h of z. Okay? So This is really the systematic way to do this. And once you get the hang of it, it's so straightforward. Okay? And then the third piece of it, well, the third piece of information is that f of x, y, z right now is equal to x, y, z plus g of x, y, g of y, z, which is only a function of z, h of z. Right? This I sub into that expression there, df dz is equal to p. So that tells me d by dz of x, y, z plus h of z, this is truly only a function of z now, is equal to p, which is xy. Well, the left-hand side is xy plus dh dz, and you could use the total derivative because h only depends on z, or just stick with the partial derivative to make your life not any more challenging. This says xy plus dh dz is equal to xy. That means dh dz is equal to 0, and that means that h is equal to a constant, a true constant. You're always going to get a constant in the end because the potential function is always arbitrary up to a constant. Okay? Just like the voltage is always arbitrary up to an additive constant. And so in this case, f is equal to x, y, z plus any arbitrary constant. And the gradient of this thing is the vector field. Okay? So that's how you do this stuff. I am going to do, this was 16.3, I think, right? Clearly, I don't know the order of the book. So we are going to learn about curl and divergence and Green's theorems, part 1 and part 2, on Monday and Wednesday of next week. I encourage you to read those sections carefully and even start some homework on it. I'm going to set some homework on this stuff. But if you start doing some problems ahead, you will serve yourself well. Better than serving yourself turkey, okay? Happy Thanksgiving to everyone.